Our universe is amazing, it's vast, and a mysterious place whose infinity still remains a mystery to us. From our perspective, if we look, we can see up to about 46 billion light years in every direction. This is what we call the observable universe. Wherever we look in space, our universe appears to be filled with stars and galaxies. But are all these things that we see really unique? Is it possible that if you look at a distant galaxy in one direction, then in the opposite direction, the same galaxy might also exist far away? Is this universe itself an infinite loop? And if we travel in a straight line in this universe, will we end up at the same starting point? Will there be a starting point that will stop us from going beyond a certain point? You can think of it as a kind of wall at the edge of the universe. And if that's the case, then what would be on the other side of that wall? And we'll learn all about this in today's video. Although it might sound strange, both cases could be possible here. You can keep traveling in a straight line forever in this universe, and something could also stop you. And all of this will depend on the expanding universe, which in itself is a mind-boggling concept. Let's do this. When we look at a distant object in the cosmos, we don't see it as it is right now, but rather we see it as it was in the past, when the photons of light left from there. From our perspective, the Big Bang happened about 13.8 billion years ago, and our measurement is extremely precise. That means the age of our universe is about 13.8 billion years, and all the other objects found in it that we can observe are not older than this. The light from that object only shows you information from when it began its journey to Earth. That means you are actually looking at the past of the Earth. Similarly, if you look at the Earth from the Moon, you will see the Earth as it was 1.3 seconds ago. If you are on Alpha Centauri, you would be seeing the Earth as it was 4.3 years ago. And if you are in Andromeda, you would be seeing the Earth as it was 2.5 million years ago. But the age of the universe will be the same everywhere you go, exactly the same. This same concept applies when we are observing another object from Earth. But when we move beyond the Moon, planets and galaxies to larger scales like the local group, an extra factor comes into play, and that is the expansion of space. If we talk about the 20th century, the discovery of the expanding universe proved to be a major revolution in our understanding of the cosmos. This factor is not visible at smaller distances, but if the distance is greater and the object is farther away, it is moving away from us that much faster. There are mainly three reasons behind the redshift observed in our universe. The first is when the source and the observer are not static but are moving relative to each other. The second is when light has to pass through a very large gravitational potential. And the third is the expansion of space between two objects. Here, the first two reasons are the relative movement and the gravitational potential. Both of those work over short distances, but the expansion of space works on a cosmic scale. There are many important reasons to study the expansion of the universe, like tracking cosmic history to understand how the universe went from a dense and hot state to a uniform shape. This helps us understand what can happen over that period. And ultimately its end as well. Now you must be wondering what all these things have to do with us traveling in a straight line in the universe. Are we straying from our topic? Not at all. Actually, this is the only way to reach the answer to our question. So let's first take a condition where you are traveling in a straight line in this universe forever. in a universe that is not expanding, that is a static and unchanging universe. Friends, when it comes to a static universe, everything becomes theoretical because practically our universe is not static. Here, everything will depend on the topology of the universe. That's right, Einstein's general relativity made us realize that space is not a rigid three-dimensional grid. Rather, it is a flexible space made of matter and energy in which curvature keeps forming due to energy and matter. And on this basis, space can be positively curved, negatively curved, or even flat. See positively curved space. It can be finite and closed in this way, although it might seem strange to you, but a flat surface can also be finite and closed. For example, by giving a long cylinder a donut shape, we can resemble a flat universe which is both finite and closed. Now here, in non-expanding space, we have two possibilities. First, either the universe will be finite and closed. In this, if we travel in a straight line, after some time we will end up at the exact same spot where we started from. Even if the shape of our universe is weird like a Mobius strip or a Klein bottle, eventually we will end up at the same place where we started our journey. The second possibility is that the universe will be infinite and open. In this, if you go in a straight line in any direction, you will always see new space. You will keep going in a straight line, but space will never end, no one will stop you, and if you want to come back to your starting point, you will have to repeat the same journey in the opposite direction. Although this may sound simple, it is an important and very significant property of the universe. Apart from this, when scientists observed everything present in the universe in every possible way, gas and plasma which we could map, radiation emitted by stars, molecules, and even the Big Bang, we tried to find repeating patterns everywhere in this universe so that we could prove that the universe is finite at a certain scale, but we didn't find any success. From this, we understood one thing, that there are no repeating structures present in this universe. The things present in one direction are not seen in the opposite direction. Even in the early times of the universe, we didn't find anything in the universe that matched with any other region. So now we come to the most important but a complicated reality that this universe is not static, so all our simple ideas can't be applied here. In fact, it's expanding, but we can't simply call it expansion. There is matter and energy in the universe, so along with expansion, it's also gravitating. So from here, you can figure out some possibilities. The first is that if the gravitating effect is more powerful, then the universe will expand for some time. It will reach a maximum size and then start contracting again, causing the entire universe to collapse back into a small point. And this event is called the Big Crunch. And this event is called the Big Crunch. And the third possibility is that if the gravitating effect balances the expansion, then this universe will become stable at one place. Then it will neither expand nor collapse, which is the first possibility where the gravitating effect is greater than the expansion. It tells us that you can never travel in a straight line forever. This universe will exist only for a finite amount of time. So here, if you travel in a straight line, you might hit a wall, and that might be the wall of time. If this is the reality of our universe, then this journey will truly be amazing. But if the second and third options represent the reality of our universe, then we will just keep traveling through space. Every time, a new space will appear before us. However, because of gravity, the expansion rate will keep slowing, allowing us to see more galaxies. And eventually, after overtaking all of these, we will reach a situation where once again we will have two options. If the universe is infinite, our journey will continue forever into new space, and if it is finite, we will come back to our starting point again. However, this space, travel, and distance will be extremely huge. But even these scenarios we've discussed still don't accurately describe our expanding space. Actually, the universe we live in is dominated by dark energy. Dark energy is a form of energy that is inherent in the fabric of space itself and always maintains a constant energy density. No matter how much space expands, the density of dark energy in the fabric of space never decreases. This shows that the expansion rate will always remain positive and finite, and this has made our understanding even better. This means that if you look at a galaxy right now that is not gravitationally bound to us due to the expansion of space, after a certain distance you will never be able to reach that galaxy. It will disappear from our reach. Then it won't matter at what speed you are going towards it, even light will never be able to reach that galaxy. We have covered this phenomenon in this video. To understand it, you should definitely watch this video. You will find the link in the I button above and in the description box below. And here we get our answer that if you set out to travel in a straight line in the universe, you will keep traveling only through time forever. Because due to the expansion of space, you will barely be able to cross even a small part of our observable universe. This really scares us that we can't make intergalactic journeys so easily. This is a cosmic horizon just like the event horizon of a black hole. The things that are on this side of the horizon, we can reach them, but those that are beyond it are getting farther and farther out of our reach. And this horizon is at 18 billion light years. The things that are beyond this distance are already out of our reach. In this entire observable universe, only 6% of objects are such that we can actually reach them. Thousands of stars cross that horizon every second. By crossing it, our universe is continuously getting smaller. If we talk about the answer to our question, then the shape of space, its curvature, topology, whether it's open or closed, finite or infinite, none of these things matter. If you set out on a journey in a straight line in the universe, you will get trapped in the whirlpool of ever-expanding space for eternity. And all of this will happen because of these reasons. First, our universe is expanding, and second, dark energy is continuously accelerating the expansion of the universe. Third, it's been 13.8 billion years since the Big Bang, and because of space expansion, it has already spread to 93 billion light years. And fourth, as far as we have seen, this universe does not repeat anywhere. Just like we can circumnavigate the Earth, we cannot do the same with the universe. Yes, it is possible that on a very large grand scale, the universe is finite. But what difference would that make? We will never know. No matter how much we travel in this universe, a very large part of it will always remain out of our reach. Because limits like the cosmic horizon don't let us go beyond a certain boundary, it feels like this universe is stopping us from going further. In our solar system, Earth is the only place where any kind of life has flourished. Now, whether you call it a coincidence or something else, this life is not here because of any one specific thing. Rather, there is a long list of reasons behind it, one of which is the occurrence of day and night and the seasons here,
which we all know are formed because of the Earth's motion.
When the Earth rotates on its axis, day and night are formed, and when the Earth revolves around the Sun, seasons are formed. It rotates about 360 degrees, then one day is completed, and in a year, our Earth travels about 1 billion kilometers. Around our Sun, it doesn't matter where you are on Earth, all of us. Along with this, we are traveling in this universe at an insane amount of speed. If I tell you that you are traveling in space at a speed of 300 kilometers per second, you might not believe it. And that's why in today's video, we are going to understand our speed. Obviously, the speed and motion are quite complicated, so we'll have to go from Earth and even beyond into space. So today, you'll be able to learn a lot about how our universe works. So let's find out how fast you're traveling in space. We know that besides Earth, our Sun is also orbited by other planets, asteroids, comets, and other things. Then this entire solar system together is orbiting the central black hole of our galaxy, and on an even larger scale, our Milky Way is traveling through intergalactic space with its local group. So by combining all these things, we will calculate a final cosmic motion. But remember one thing, motion is always relative, meaning it depends on what we are measuring the motion and speed of and with respect to what. For example, two passengers sitting in a train are not in motion with respect to each other, but for the person standing outside the train, both those passengers are in motion, meaning speed and motion are relative entities. So let's start first with the Earth's spinning speed, that is, the Earth's rotation on its own axis. Here, the answer might seem simple to you, but it's actually a bit complicated. Because of the Earth's rotation, your speed on it will depend on where you are on the Earth. We assume that our Earth is a rigid body whose shape doesn't change much. Because of its motion, it completes one rotation on its axis in 24 hours. To be more precise, this time is 23 hours, 56 minutes and 4.09 seconds. Earth's average radius is 6,371 kilometers, but that's only an average. The Earth's structure includes mountains, valleys, and many other things, but because of its rotation, there is also a huge bulge at its equator. So if we talk about its precise radius, then the volcano Mount Chimborazo, located at the equator, is the farthest at 6,384 km, while its north pole is the closest at 6,356 km. That's why it is said that the Earth is slightly flattened at the poles, and because of this, if we look at the speed of a point on Earth's equator, it is around 1,676 km range, and as we move towards the poles, this speed keeps decreasing. For example, after moving 45 degrees, this speed remains at 1,183 km, and when you reach the poles, this speed becomes zero, meaning that at the Earth's geographical poles, things only rotate completely and do not travel any distance. So due to Earth's spinning, our speed on Earth depends on our position. The top speed is 1,676 km/h, while the minimum is 0. Now let's talk about how fast the Earth moves around the Sun. First, let's consider the Earth's fastest rotational speed, which is 1,676 km/h. We can translate this to 0.47 km per second. But compared to the speed at which the Earth revolves around the Sun, this speed is nothing. The Earth is about 150 million kilometers away from the Sun, and to stay stable in this orbit, the Earth has to travel at a speed of 30 kilometers per second. However, throughout the year, our Earth travels around the Sun at different speeds. When it is closest to the Sun, the Earth moves the fastest at a speed of about 30.29 kilometers per second. And when it is farthest from the Sun, its speed decreases by about 3%, and it travels at a speed of 29 kilometers per second. In the same way, the innermost planets have higher speeds. For example, Mercury, which is closest to the Sun, travels at about 47 km per second, and the planets that are farther away move much slower. For example, Neptune orbits the Sun at a speed of 5.4 km per second, but for now, we have found out Earth's speed, which is a maximum of 30.29 km per second. However, compared to the upcoming cosmic motions, even this speed of Earth is nothing. So now we will talk about how fast our entire solar system is traveling around the center of the Milky Way. As we know, the closer something is to a massive body, the faster it has to orbit to maintain its position. Well, something similar happens in this case too. Here, there are billions of stars that are being pulled toward the center of the galaxy. Similarly, our Sun is also located about 27,000 light years away from the galactic center. This distance is so vast that it takes the Sun about 220 to 250 million years to complete one orbit around the galactic center. This means that the last time the Sun was in the same position in the Milky Way, some of the first dinosaurs had just started to evolve on Earth. It is estimated that our Sun is traveling around the Milky Way at a speed of about 220 kilometers per second. That's about 7 times faster than the speed of the Earth. But there are a lot of uncertainties here, like our solar system is extremely large, and then the Milky Way is a whole galaxy. We can't exactly trace the motion between them because everything here is moving. And after this, if we leave the solar system and talk about the Earth, this uncertainty increases even more. Also, the solar system's plane is tilted about 60 degrees to the galaxy's plane, significantly affecting Earth's speed. Because of this tilt of the solar system, the speed of the Earth keeps changing. When the Earth moves in the direction of the solar system's movement, its speed increases to 237 km per second, and when it moves in the opposite direction, it remains only 208 km per second. So in this way, the difference in orientation affects the speed of our Earth. And here, because of the motion of the solar system, the speed of our Earth goes up to a maximum of 237 kilometers per second. Now let's talk about our own Milky Way galaxy, which is traveling within its own local group. Force works in such a way that the more massive two bodies are, the greater their gravitational attraction will be. And this same massive influence on cosmic scales also helps us achieve insane speeds. In our local group, there are a total of 60 galaxies big and small, among which the Andromeda galaxy is the largest and is in second place. Our galaxy, the Milky Way, is 2.5 million light years away from the Andromeda galaxy, and it is about twice as massive as our Milky Way. Because of its great distance and size, it is very difficult to determine exactly how it changes its position over time, so that we can find out its speed. Because here, we're talking about a time scale even beyond the human time scale, but still, by studying the cosmic blue shift in spectral lines, what we've observed tells us that Andromeda is coming toward our sun at a speed of 301 kilometers per second. And when we looked at our direction in the Milky Way, according to that factor, Andromeda is moving toward our galaxy at a speed of about 109 kilometers per second. And now we'll see how our local group is traveling in intergalactic space. Finally, at this grand scale, things get really weird. Here, galaxy groups, clusters, superclusters, and even groups of superclusters are shaping this universe. The areas of space that are very dense pull us towards them with their massive gravity, and the areas that are empty, that is, the voids, repel our local group. On one side, the Virgo supercluster is pulling us towards itself with its massive gravity, while on the other side, the voids in space are pushing us towards the Virgo cluster. And this speed is really insane. We are being pulled at a speed of about 300 kilometers per second, and at the same speed, the voids are repelling us. Because of this, our local group is getting a total gigantic speed of 600 kilometers per second. So overall, if we summarize, our total speed is made up of these components: the Earth's motion around the sun orbiting the galaxy, the Milky Way moving towards Andromeda, and finally, the local group moving towards the overdense regions. So here, we have covered a very large scale. But if we talk about a particular direction, our total motion is towards the constellation Leo, and we are traveling towards the constellation Leo at a speed of 368 kilometers per second. And apart from this, if we look at the scale of the local group, we are traveling towards the other large structures at a speed of about 627 kilometers per second. Another important thing that we learned here is that motion is relative. If we want to know our speed in space, then we also need to know with respect to what we are measuring that speed. Here, our frame of reference keeps changing. Nothing in this universe is static. Everything, from the smallest to the largest scale, is moving. But for now, these are our limits. And no one knows how big this universe really is, what our actual speed is, or if this speed even truly exists. Or not. Loneliness is truly dangerous. That condition where you can't see anyone for miles, there's no one to talk to, no one to help, and you are badly entangled in circumstances. Just thinking about it is scary. What if suddenly every human being disappeared from this earth? If only you were left behind, that loneliness would eat you up from the inside. And maybe in that eternal loneliness, you would even start talking to the silence. You would be alone in your house. You would be alone in your city, in your country, and even on this earth, plunging into this terrible darkness. What scares us even more is that we haven't found any neighbors in this vast universe yet, and we still feel this loneliness on a cosmic scale today. This whole scenario becomes even more frightening then, when you realize that no matter what you do, You can't stop that coming loneliness. It will happen anyway, and something like this is happening in our universe too. Our universe is constantly disappearing. Every moment we are becoming more alone in this infinite universe. And in the coming time, there will be a moment when, even if we want to, we won't be able to reach even the nearest star. Even if we travel at the speed of light, knowing all this, we still can't do anything. We can only watch as this universe makes us powerless, imposing countless natural laws like the speed of light on us, making us alone. Today's video will tell the story of our universe for billions of years to come. And I think this video goes beyond our present time. It's just to forget everything and bring some deep thoughts to your mind. It's to understand how this universe actually works, and maybe these are questions we've been searching for centuries. So let's make a start today as well. You can close your eyes if you want. Your imagination will make this video even better. It's been almost a century since we found out that our universe is expanding. By the way, the story behind the expanding universe is quite big. But we all know that Edwin Hubble observed the redshift of galaxies moving away. He studied that the farther a galaxy is from us, the faster it is moving away from us. This was a frightening thought for all those who imagine a future where humanity will rule the entire universe. When there are no galaxies visible far away in the universe, when the sky will appear black and not a single star will be seen, then where will that advanced civilization rule? And this very question was frightening all of them. Many times people make mistakes in understanding this theory of the expanding universe. Their argument is that if the universe is really expanding, if stars and galaxies are moving away from each other, then how can our neighboring galaxy Andromeda collide with us? So here, we need to understand this theory, which says that galaxies are not physically moving away from each other. Rather, the space between the galaxies is expanding. Objects in the universe that are there won't see its effect. But in the part of space where there is nothing for a long distance, when the fabric of space expands there, its effect can also be seen. This theory of the universe's expansion was proven just 20 years ago. But by then, we had already learned that as time and distance keep increasing, this expansion of space will also keep increasing continuously and just as rapidly. A galaxy that is moving away from us today will get even farther from us after some time, and because of this, it will move away from us even faster, and this process will keep continuing. Eventually, a time will come when it will go so far beyond our reach that even thinking about reaching it will be impossible. We won't even be able to catch the light coming from there, and that galaxy will disappear from our view in this infinite universe. The space between that galaxy and our galaxy will start expanding faster than the speed of light, because of which we will never be able to see that galaxy again. And believe me, this universe is disappearing like this, and we can't do anything about it. When you look at a star in the sky above, if that star's light took 100 years to reach you, the star is 100 years old. Light years away, and the reason is that the speed of light has a limit. It only travels the distance of 1 light year in a year. But when you're looking at the light coming from a galaxy, which has reached you after traveling for about 100 million years, it doesn't mean that the galaxy is 100 million light years away from us. Here, your calculation will turn out to be wrong. In reality, that galaxy will be much farther away than this. The reason is that when we talk about smaller scales, things are often gravitationally bound. Stars come together to form clusters. The light that travels from here to reach us takes a lot of time. And in the meantime, the expansion of space also does its work, so the light that reaches us is also affected by the expansion of space. That is, along with space, we call this cosmic redshift. If light is being emitted from somewhere, it has a particular energy and a particular wavelength. And we expect that when we receive that light, it should have that same particular wavelength. And this would have been possible if the universe was not expanding, but in reality, that never happens. The farther a galaxy is, the more redshifted the light coming from it appears to us. Now we know that the universe is expanding and will continue to do so. But with this information, we can find out how the universe has evolved over time and what exactly the universe is made of. Scientists analyze light from distant regions of the universe, measuring redshift, actual and apparent size and brightness, then use this data to reconstruct the universe's entire expansion history. And it was also found out what kind of energy and matter are present in this universe. This entire universe is made up of 68% dark energy, 27% dark matter, 4.9% normal matter, 0.1% neutrinos and antineutrinos, and about 0.008% photons. And when we found out the components of this universe so precisely, the law of gravity was applied to them, and Einstein's general theory of relativity brought a dark chapter of this universe before us. First, these laws were applied to the dark energy dominating universe, and the results we got were shocking. First of all, the galaxies that are not gravitationally bound to us will eventually disappear one by one. They will keep moving away from us faster and faster, and the space between them will keep expanding more and more rapidly. And this led us to a conclusion that is even more disturbing. This means that a time will come when, due to the expansion of space, a photon leaving our galaxy and heading toward another galaxy or coming from that galaxy toward ours will never be able to reach us or them after a certain distance. It will just keep traveling, keep moving through the fabric of this ever-expanding universe, but it will never be able to reach anywhere, because space will be expanding at a speed much faster than the speed of that photon. Think of it like it's running on the spot, but it will never be able to reach anywhere. If this thing can trap a photon like this, then we humans aren't even at 10% of the speed of light yet. But just think about it, if we set out on an intergalactic journey and got trapped in such a web of expanding space, would we end up wandering there for eternity? We wouldn't be able to reach the other galaxy, nor would we ever be able to return home. This is nothing less than a terrifying nightmare. At that time, even space itself will feel no less than a black hole to you. The only difference is that here you'll be able to struggle, you'll get some time to stay alive, but you'll never be able to get out of here. If we talk about the present, the radius of our observable universe is about 46 billion light years, and that magical distance, meaning the reachable limit, is only 18 billion light years. You'll definitely be shocked to hear that already 94% of the observable universe is out of our reach, and only 6% of the observable universe is within our reach. If there's a galaxy at the edge of that, then if we set out to explore it today, we could reach it, but we'd have to travel at the speed of light. Otherwise, it too will disappear from this universe just like that. This means that every second, about 20 to 60,000 stars are moving out of our reach. The light that left that star this second will reach us someday, no matter what. But the light that leaves that star on the edge in the next second will never be able to reach us. This thing also feels scary to us. It's creepy, it's disturbing, and all sorts of strange thoughts start coming to mind. But we can also think about this in a positive way, that the universe wants to tell us that every single second of life is very, very precious. If we want to do intergalactic travel, if we want to go beyond our local group, then we have very little time. Every single second, 7,000 stars are disappearing from our reach, places where maybe we could go. The more we delay, the more opportunities we will miss. There are about 2 trillion galaxies in the observable universe, and out of those, 94% have already moved beyond our reach. Of the remaining 6%, even that number is continuously decreasing. Another perspective to look at this is that no matter how big our universe is, We only have a small part of it as the observable universe, which we can see, which we can observe, and even in that, we can only reach 6% of it. So what's the use of such a universe where we can't even go? This raises a lot of questions in our minds. Are these limitations being set by the universe itself, or is there someone else behind it who is stopping us from exploring this universe? And if we don't develop intergalactic travel soon, to get out of our local group, the entire human civilization will be confined to just its local group. The whole universe will slip out of its hands like sand, all the other galaxies will slowly disappear from sight, and the sky without stars will look completely dark, scary, and strange. Many questions come to mind. Sometimes it feels like, why is there a speed of light limit? Can't we do anything about it? Will we always be trapped like this? Yes, of course these questions don't really matter to us because this is a long process that takes billions of years. We won't be able to see any of this. But it's these very questions that have brought our science to where it is today. What are your questions about this universe? And can we prevent the loneliness of this universe from happening? Be sure to share your opinion with us in the comment section. I hope you liked today's video. If you enjoyed it, please like it and be sure to share it with your friends. For more informative videos like this, make sure to subscribe to the channel and enable the bell notification. Friends, we'll meet again soon with another informative video like this. Until then, stay curious, be happy, and goodbye.